All right, let's jump right into this explainer on coordination compounds. If you're prepping for your JEE or NEET exams, or honestly, if you just want to completely demystify this notoriously tricky area of inorganic chemistry, you are in the exact right place. We're going to break down the molecules that literally form the backbone of bioinorganic chemistry and modern industry.
Here is our roadmap for today. We are covering 1. Werner's coordination theory, 2. Double salts versus complexes, 3. Anatomy of a complex, 4. IUPAC naming and geometries, 5. Bonding theories, specifically VBT and CFT, and 6. Real-world applications. Let's get to it.
Starting off with Section 1, Werner's coordination theory, the massive chemical anomaly that basically gave birth to modern inorganic chemistry.
Okay, picture yourself as a chemist back in the late 19th century. You dissolve a compound in water, fully expecting it to split completely into simple ions, because, well, that's what normally happens. But mysteriously, with certain transition metal compounds, a solid core just remains firmly bonded together. It's like a microscopic locked safe that absolutely refuses to break apart, no matter how much water you throw at it. So why does this happen?
The guy who cracked this code was Alfred Werner. He was essentially a chemical detective who proposed some incredibly revolutionary ideas about how atoms and molecules link together, completely upending everything the scientific community thought they knew about valences.
And Werner was an absolute prodigy. In a breathtaking span of just 3 years, from 1890 to 1893, he formulated this groundbreaking coordination theory. He then spent the rest of his career gathering the experimental proof to back it up, characterizing a massive number of compounds using really simple techniques. All of this incredible work made him the very first Swiss chemist to win the Nobel Prize in Chemistry in 1913.
To prove his theory, Werner ran this brilliant experiment with cobalt chloride ammonia complexes. He added excess silver nitrate to these solutions, and the results were super revealing. The varying amounts of silver chloride that precipitated out, ranging from 3 moles down to just 1 mole, proved something profound. It meant that certain chloride groups were ionicizable, but others were tightly bound to the cobalt ion along with the ammonia. They created a single, non-dissociating entity that just totally ignored the silver.
This brings us to a massive, high-yield concept for your exams. Werner concluded that in coordination compounds, metals show 2 distinct types of linkages. First, you have the primary valence. This is ionizable and satisfied only by negative ions. Think of it like a heavy winter coat that the molecule can easily take off. But then you have the secondary valence. This one is non-ionizable. It's the molecular skeleton. It binds directly to the metal, dictates the actual 3D spatial shape, and is a fixed number for that specific metal. Today, we call this secondary valence the coordination number.
Moving right along to Section 2, double salts versus complexes.
This is a classic trap on exams, so let's clear it up. What is the difference here? Well, double salts, like carnallite or Morse salt, are basically completely destroyed in water. They dissociate entirely into simple ions. Complex ions, on the other hand, do not. If you drop a complex ion, like the ferrocyanide ion, into water, that core coordination entity remains perfectly intact. It keeps those cyanide ions bound incredibly tightly to the iron.
All right, Section 3, Anatomy of a complex. Getting this vocabulary down is absolutely critical for scoring well.
At the absolute center of it all, you have the central metal atom or ion. It sits there surrounded by a fixed number of groups in a highly specific geometric arrangement. The key takeaway for your test is that this central metal acts as a Lewis acid. Its entire job is to accept electron pairs from the partners surrounding it.
And the partners donating those electrons, we call them ligands. Ligands can be simple single-donor ions like chloride, those are unidentate, or they can be massive macromolecules like proteins. You also need to watch out for the sneaky ones, ambidentate ligands. These are ions like nitrite or thiocyanide that can actually coordinate through 2 entirely different atoms. For instance, nitrite can bind through its nitrogen atom, or it can flip and bind through an oxygen atom.
This leads us to a super common comparative question. If the central metal is surrounded by only one type of donor group, say it's just covered in ammonia ligands, that's called a homoleptic complex. But if the metal mixes and matches its donor groups, maybe grabbing some ammonia and a couple of chlorides, then it's a heteroleptic complex.
Let's head into Section 4, IUPAC naming and geometries, the universal language of chemistry.
You've got to have these IUPAC rules down cold, because naming coordination compounds systematically is 100% going to show up on your exam. The rules go like this. Always name the cation first, then the anion. When you list your ligands, do it in strict alphabetical order before naming the metal. For anionic ligands, change their ending to an O, like chloro. Use simple prefixes like di or tri for multiples. But here's the trick they use to catch you. If the ligand's actual name already has a number prefix in it, you have to use bis, tris, or tetrakis instead. And lastly, never forget to put the central metal's oxidation state in Roman numerals right at the end in parentheses.
But naming is only half the battle. You also have to picture these things in 3D. To figure out the spatial shape, the coordination polyhedron, you just count up the ligand donor atoms directly bonded to the metal. Yep, that's the secondary valence Werner was talking about. If your coordination number is 6, you're almost certainly looking at an octahedral geometry. If it's 4, it's typically going to be tetrahedral or square planar.
That takes us to Section 5, bonding theories, specifically valence bond theory and crystal field theory.
Werner was a genius, no doubt, but his theory had limits. It couldn't explain why these complexes have directional bonds or why they have such specific magnetic and optical properties. For that, we rely on modern quantum mechanics, using two complementary theories. Valence bond theory, or VBT, is fantastic for predicting geometry and magnetic behavior using hybridized orbitals. But crystal field theory, or CFT, treats the ligands as negative point charges. And CFT is absolutely brilliant at explaining optical properties and the vibrant colors these compounds produce.
Let's actually see crystal field theory in action with the titanium hexaaqua complex. This complex absorbs blue-green light from the visible spectrum. That specific energy is just enough to excite a single electron from a lower energy T2G level up to a higher, empty EG level. We call this jump a DD transition. Because the complex absorbs the blue-green light, the complementary color, which is a really brilliant violet, is what bounces back and hits our eyes.
Let's wrap things up with Section 6, Real-World Applications. It's time to take these abstract concepts and see why they actually matter in the real world.
Without coordination compounds, life as we know it literally wouldn't exist. The pigment that powers photosynthesis in plants, chlorophyll, that's just a coordination compound built around magnesium. The hemoglobin carrying oxygen through your veins right now, that's a coordination compound centered on iron. Vitamin B12 is built around cobalt. Plus, tons of crucial biological enzymes use coordinated metals as catalysts to keep our bodies functioning.
And it doesn't stop at biology. Industry and medicine are just as obsessed with these compounds. We use them to get incredibly smooth silver and gold finishes in electroplating and for dyeing textiles. In old-school black and white photography, hyposolution works by forming a complex with silver bromide to fix the film. In the chemical industry, the Wilkerson catalyst drives alkene hydrogenation. And in medicine, it's a real game changer. We use chelating agents like EDTA to safely trap and remove toxic lead from the body, and platinum complexes like cisplatin are actually used to inhibit tumor growth in cancer patients.
So, as we finish up this explainer, I want to leave you with a thought. We already know that certain compounds, like metal carbonyls, feature this incredibly unique synergic bonding where sigma and pi bonds literally reinforce each other. Knowing that we can manipulate these kinds of atomic interactions, how do you think the unique bonding properties of these complex molecules will be engineered next to solve the massive medical, environmental, and industrial challenges of our future? Really think about that. Thanks for hanging out for this explainer, and good luck with your studying.